Hello, in this video I'm going to go through a fairly complicated question on moments of inertia and rotational movement. And I'm not just going to fly through it, I'm going to try and clarify some of these issues that we've gone through in other videos of why we're doing everything in this way and what this moment of inertia means and all the rest of it. So yeah, I'm going to take my time over this one. Right, so what have we got in the text that isn't in the description? What is in the text isn't in the diagram. I mean, in this first part, we got a uniform rod AC, yeah, mass 2m, that's not in the picture, length 8a, they've marked that on. Point B lies where it does according to that, right? So it's just this 2m that we've got add on there, add on to the picture. So find the moment of inertia of the rod about an axis through the point B. So they're setting us up here for rotating this rod about an axis going through B, because we've seen in our previous videos, and you're probably fairly happy with this bit, I would imagine, that if you're going to rotate an object, the axis of rotation really does matter because it affects the distribution of matter around the point of rotation. So in this case, by rotating about B, the stuff at C is going to have more kinetic energy and momentum than the stuff at A because it's further away from the axis of rotation, so it has to go through a longer path in order to complete one revolution. Now it's a rigid rod, so everything's completing a revolution in the same amount of time, but C has to travel further, so if it's got to travel further in the same amount of time, it must be going faster, so it must have more kinetic energy and it must have more momentum. So we know that the axis of rotation matters when we're describing things that are rotating. So we have to have some way of quantifying or describing this distribution of matter about that point of rotation, which is what we're doing with a moment of inertia. And this will drop in the next part of the question as well. So let's just do it here and then see the impact on the next bit of the question. So let's remember moment of inertia. So we're adding up for each point. I've gone through this in a previous video. I'm not going through all the detail on this bit here. We're adding up the mr squared for every little chunk along the rod. So we're breaking it up to bits and we're turning this into an integral. So we're saying the moment of inertia is going to be the integral along the length of the rod. So we're going to go from minus 3a to 5a of the little bit of mass that we've got for each little chunk of the rod. So if we take a little bit of length dr, multiply it by the whole length, which is 8a, and then multiply that by the total mass, that's our little m here in our sort of generic formula. That's our fraction of the mass, and then we need to multiply by r squared. So we're just going to be integrating this. That's going to come out as, let's take our constants outside. We've got m over 4a. I'll do the integral straight away because it's pretty straightforward. We're just integrating r squared. So we've got r cubed over 3, and we're going from 5a down to minus 3a. So that is going to be 125 a cubed over 3. So let's just deal with the numbers because we know we're going to get an a squared. So because that's going to cancel with the other a. I'm just trying to save some space here. So we've got ma squared. We're going to have 125 plus 27, which is 152 divided by 4 and divided by 3. So 152 over 4 is 38. So we've got 38 over 3 ma squared. So that's a pretty simple integral, and this isn't really causing us any problems at the moment. And let's see how this is really dropping into the rest of the question, this moment of inertia that we've worked out at this point. Right, so what's happening next? We've now got the rod held in equilibrium on a horizontal table with a rod perpendicular to the edge of the table. Section BC projects over the edge. Right, it's released from rest, begins to rotate. When the rod has turned through an angle theta, it's not yet begun to slip. Right, so they put the centre of mass over the edge of the table, and this is part of the reason that it's going to start rotating round. We've got this weight hanging over the edge. We've got a reaction force here, normal to the edge, and we've got some friction going on, which may or may not be limiting, which must be going up the rod because the rod would tend to fall down. We've clearly got motion going clockwise around point B. So if we were going to try and approach this, say we didn't know anything about moments inertia or anything like that, and we were going to try to just describe this using Newton's laws as we would have done before, all the linear stuff, all your F equals ma and things like that. Well, we'd have to start looking, all of these points are in motion apart from B. So we'd have to look at every single point and think, well, how is that going to be moving according to the forces that are being applied to it? Because these forces are going to be felt, the F, the R, and the weight, all of these reaction force, friction, and weight are going to be felt throughout the rod. All of the points are going to be experiencing these because the rod is rigid, so they get translated along the length of the rod. Yeah, we haven't just got whatever the little bit of matter sitting at B is feeling this reaction force and none of the rest of it does. We're taking for granted in this the rigidity of the rod, and the fact that the rod is rigid, all of these points are going to be feeling R as an effect, which is making it rotate round. So we've got this transmission of force throughout the length of the rod. So we'd have to look at every single point and think, well, what exactly is happening in terms of how quickly it's moving around this point B, which is going to be to do with where that bit of matter is, how far away it is from B. And then we're going to have to start integrating the effects of F equals ma on every single point. Well, this is why we're doing the moment of inertia already, because we've already taken into account that distribution of the matter along the length of the rod. So all of this stuff here that we've worked out in moment of inertia, that's why it's so useful. Now we have got this circular motion going on. So up until the rod starts slipping, it's fixed at B. So if it could keep going round and round and round, I mean, it can't. You've got a table in the way and eventually it will just fall off. But at least in the beginning, the center of mass of the rod is going to be moving in a circle around B, because that's the fixed point. In fact, every point along the rod is moving in a fixed circle around B of a different radius every time. So this is what we can be looking at in order to describe what's going on. And because it's in that pure circular motion, if we describe everything in terms of circular motion and rotation, then we can just use these simplified formulae using moment of inertia. There's no translation going on, so we don't have to add anything else in. We won't have to do any more integrals or anything because it's already built into the equations. So let's compare. So say we're used to doing half mv squared for our linear kinetic energy. Well, if something is moving perfectly in a circle, we reduce this rod down to the center of mass and think, because we're used to doing that previously, you take extended objects and say, well, we can treat that the same as a point at the center of mass moving around. We reduce this rod down to a point at the center of mass. That center of mass is traveling in a circle around B. So we can say that, V is equal to omega r. That's from our circular motion. So our half mv squared is going to become a half mr squared omega squared. And this mr squared is the moment of inertia of the object. So we've now got a half I omega squared. So it's dropped straight into quick description in rotational sense, from a moment of inertia sense, moment of inertia, our rotational mass. So let's use this for what they're going to want us to do in the next part of the question. They want us to show that the angular speed of the rod is all of this. So we can do our conservation of energy in the same way as we normally do. You say, right, the center of mass has dropped from, it started off horizontal and now it's dropped by some amount. So what exactly what's our triangle going on here? This angle is theta, that distance is A. So we've dropped by an amount of A sine theta. So our change in gravitational potential energy is going to be mgh. So we've got 2mg, and then we're dropping by A sine theta. That's our h. So that's our change in GPE. And because this is just moving in a circle, we can use this half I omega squared as our rotational kinetic energy. Instead of previously we've been using this if it was moving linearly. If it was moving both in a circle and being translated, we've got some awkward combination of the two, but we've got a fixed axis of rotation, so we can just say it's a half I omega squared. Well, we know what I is, so let's just whap all of this in and then see what we get, because this is going to be what, 19 ma squared over 3 times omega squared. So we can cancel the m's, we can cancel one of the a's on either side, and now we've got the omega squared is equal to 6g sine theta over 19a, which is what they wanted us to show here. They just square rooted it. So that's all good. So you can see the advantage of doing that. If we hadn't have known anything about moment of inertia, we just would have pushed ourselves into doing this integral without having really thought things through, because that's what we'd end up having to do in order to add up all of the little bits of linear kinetic energy that were going on. So that's all looking fine and dandy. Right, now we need to find an expression in terms of a, g, and theta for the angular acceleration. Right, this is just an exercise in calculus. So we've got here, I mean, this is another way of writing it, is theta dot squared we've got here, and we need to get theta double dot. So we're going to do, well, let's differentiate both sides on this. So if we differentiate theta dot squared, we're going to get 2 theta dot theta double dot. Hopefully you're happy with that with your calculus. If not, go to some of the calculus videos, because I'm not going to explain all of this here. And then we can do the same with this. We're going to have 6g cos theta over 19a multiplied by theta dot. Cancel the theta dots on either side. We can then divide by 2, and we've now got the angular acceleration is 3g cos theta over 19a. So that's fairly straightforward. That's just an exercise in calculus rather than anything to do with anything to do with rotation, really. So that's good. So that's taken us through the third part of the question. Now we got the really big bit at the end, so I'll have to make a bit more space for this one. Okay, I've done a quick bit of jiggery pokery there to get some space to move on to the last part. So now we need to show that the rod begins to slip at some particular angle here. This tan theta is 16 over 25 mu, where mu is the coefficient of friction. Okay, so up until the point of slipping, we've still got this centre of mass is moving round and round in a circle. So this is where everything is just crucial in this. So we know if it's moving in a circle that we've got V equals omega r. Differentiate both of these, we know that our acceleration is going to be equal to our angular acceleration times r. Or another way of writing that, that's theta double dot r. So we've worked out theta double dot. We did that in the last bit. So we can certainly use that in working this out. So we know we've got a couple of things happening here. You know, when we're looking perpendicularly to the rod, we've got now a new form of Newton's second law, that rather than doing our straight F equals ma, we can say, well, we know that we've got this new way of writing down what A is, and this is going to be, well, yeah, this is our new Newton's law of motion. We can just sub that straight in. That's when we're looking perpendicular to the rod. But when we're looking parallel to the rod is the motion of the center of mass, is the centripetal motion of the mass. Yeah, you think of this, we look at, looking on our diagram here, for this point, this center of mass to be going round and round and round B, we need to have a centripetal force, which is going to be keeping it moving in that circle. So we're also going to be able to do that. So we've got these Newton's law perpendicular to the rod, and we've got our centripetal acceleration parallel to the rod. So let's go through these. So let's start with perpendicular. So looking perpendicular to the rod, what have we got? We've got R going, well, R's going in the opposite direction to the motion. You know, if we're moving clockwise, the thing that's driving the clockwise motion is the component of the weight which is perpendicular to the rod. So that is going to be 2mg, and then let's work out what our where our angles are. Right, so if that's theta, that's 90 minus theta. So it's going to be 2mg sine 90 minus theta, so 2mg cos theta. We got R going the other way, and R is already perpendicular, so minus R. So that's our net force. That's our resultant force perpendicular to the rod. But because it's moving in a circle, rather than just doing an MA, we're going to do an M, which is 2M. And then we're going to go for, well, this equation here. So instead of having our acceleration, we've got R, as in the radius from the center of the circle, the distance of the center of the mass, distance of center of mass from the center of the circle, which is A, because the center of mass is a distance A away from B. So we've got A, and then we need to multiply by theta double dot. So this is just the bonus that you get of something moving in a circle. We've got that new way of applying Newton's second law, but it is just Newton's second law with an integral thrown in, because this theta double dot contains, is a function of the moment of inertia. That's sitting inside theta double dot. So yeah, that's why we had to work all of that out in the beginning, and why we don't have to do an integral using Newton's second law at this point, because we did the integral earlier on when we worked out the mass distribution about the axis of rotation. Right, so we've got all of that, so we can say we've got all of this, so we can say what R is. R is going to be equal to 2mg cos theta minus 2ma times 3g cos theta over 19a. Right, we've got a lot of things we can do here. We can cancel those a's for a start. Let's factorize, well, we got 2mg cos theta, can actually factorize, and then we got 1 minus, so we've had that 2mg cos theta 3 over 19. So that's what, 16 over 19 multiplied by 2, so 32 over 19 mg cos theta. So that's given us what our normal reaction force is. Right, now we can go parallel to the rod. So parallel to the rod, looking at our center of mass here, what are our forces parallel to the rod, and what's going to provide the centripetal force? So the centripetal force must be coming from the dominance of F over the component of the weight going in the opposite direction. So we've got F, which is pointing towards the center, that's pointing towards B, and we're taking off 2mg sine theta, the other component of the weight, and that has got to be our that's our centripetal force. So we are still doing Newton's law on this, but we know that centripetal force, so we have to have 2m, because that's the mass of the whole thing, and then multiplied by a, because that's our radius, multiplied by omega squared. Yeah, so stick with theta dot squared. Okay, so, and we know what that is because we worked it out here in the second part of the question. So that is equal to 2ma multiplied by 6g sine theta over 19a. Again, the a's are going to cancel. So F is going to be equal to, what have we got here to, yeah, the 2mg sine theta factorizes again. So 2mg sine theta, 1 plus, in this case, what's left? 6 over 19. 6 over 19, yeah, 6 over 19. So that's going to be 50 over 19 by the time we multiply by that 2, 50 over 19 mg sine theta. So these are all things that you're familiar with, just in a, because we've done this in previous stuff. We've done centripetal acceleration in previous questions on circular motion. We've done Newton's law. We've just stepped this first bit up a little bit for working out now, because it's moving in rotation, that we can look at this angular acceleration rather than linear acceleration. But hopefully you can see how these are so similar to what you've already done. It's not a massive leap onto the next step on all of this. So anyway, we worked out F and R, and now we can do our usual bit, which again we're familiar with friction, that we're at the point of slipping. So F is going to be equal to mu R. So we need to whack all of that in. So what have we got now? We've got F, so 50 over 19 mg sine theta is equal to mu times, I can't even see where we are, 32 over 19 mg cos theta. Right, so this is all looking nice. Get rid of the 19 and the mg on both sides. Which way round do we want it? They want us to leave us with a tan. So we divide by the cos theta. So tan theta there, and we divide by the 50. So 32 over 50 mu, yeah, which is 16 over 25 mu. So that's dropped out quite nicely at the end. But yeah, this is all so close. It feels sometimes that it's a massive step getting into rotation away from the linear stuff. And sometimes, yeah, it can be tricky if you've got both things happening at once. But if your axis of rotation is fixed in space, or you can change your frame of reference to make it fixed in space, as in your axis of rotation isn't accelerating, because thinking back to our stuff with frames of reference, if it's moving at a constant velocity, we can just reset our frame of reference. We're not suddenly switching into non-inertial frames or anything like that. We're still quite happy to have this zero velocity, not accelerating frame of reference. And then great, we've just got stuff that's moving around in circles, in which case we can flip over from linear acceleration to angular acceleration, doing all of this, which means we get out of just doing linear F equals ma into angular F equals ma. We've got all our stuff that we're doing anyway with circular motion and our v equals omega r, and then we've got our centripetal accelerations as well, as we've done here. So all of that stuff just starts coming in, and we know how to do it all. It just looks a little bit scary at first because we're changing all of that terminology. But it's just saving us a world of pain of not having to continually integrate things by trying to treat circular motion as linear motion and always having a look at every little bit of a rod. You build the integral into the moment of inertia to have that angular mass, use our knowledge of circular motion, and then we've got simple equations that we can apply in the way that we've done here in order to analyze a fairly difficult problem. So yeah, hopefully that's cleared up some of the potential confusion or fear that you might have about moving into this area. I will start putting up more of these type of questions at some point, but not go through them in quite as much depth, just to get your flow going with being able to answer these quite quickly.